Hi, my name is Shannon Abraham, and in this experiment, we investigated the magnetic field produced by a bar magnet and modeled it as a magnetic dipole. The goal was to measure how the magnetic field varies with distance and to determine the magnetic dipole moment of the magnet. We then used a computational model to simulate the magnetic field in 3D and compared our model predictions to the experimental data. Our main result is that the magnetic field decreases with distance and follows a trend consistent with the dipole field, and we calculated a magnetic dipole moment of approximately 0.002077 times m squared. A bar magnet behaves like a magnetic dipole. Using this magnetic equation, we describe the magnetic field produced by a dipole. The field depends on the magnetic moment, mu, the distance, r, and the direction relative to the dipole. A key takeaway is that the magnetic field decreases approximately as 1 divided by r cubed, meaning it drops off very quickly as you move away. We used a magnetometer to measure the magnetic field at different distances from the magnet along its axis. The system is the bar magnet, and the surroundings include Earth's magnetic field and the environment. We aligned the setup to minimize interference from Earth's magnetic field and record the x component of the magnetic field at multiple distances. When far away, the magnetic field approaches zero. As we move closer, the magnetic field increases. These are some of the observations we saw. From our data, we observed that as distance decreased from about 0.12 meters to 0.085 meters, the magnetic field increased from about 2 times 10 to the power of 5t to 2.2 times 10 to the power of 4t. A logarithmic plot of natural log of the magnetic field versus the natural log of r showed a negative slope, consistent with the expected inverse cubic relationship. Using our experimental data, we calculated the magnetic dipole to be 0.002077. In GlowScript, we implemented a function called dipole_b that computes the magnetic field using the dipole equation. We visualized the field along the axis of the magnet, perpendicular to the axis and at a 45-degree angle. The simulation showed field lines consistent with the dipole pattern, spreading outward and decreasing in magnitude with distance. When comparing our model to experimental data at a 45-degree angle, we found reasonable agreements. Small differences occurred because the dipole model is less accurate at short distances, and environmental magnetic field introduced noise. Some possible sources of error include interference from the Earth's magnetic field, misalignment of the magnetometer, measurement uncertainty in distance, and the magnet not being a perfect dipole. If we did not align the experiment with Earth's magnetic field, our measurements would include additional components from the Earth's field. This would distort the data and make the magnetic field appear larger or differently directed than it actually is. If two identical magnets were placed end to end, the magnetic dipole moment would increase. Since magnetic field strength is proportional to mu, we would expect stronger magnetic field values at all distances, same general shape of the field, but larger magnitude. In conclusion, our experiment confirmed that a bar magnet behaves like a magnetic dipole. With a field that decreases rapidly with distance, our computational model aligned well with the data, supporting the validity of the dipole approximation. Thank you.